Good afternoon, miners, and welcome back to UTEP Midday News. It's Tuesday, November 11th, Veterans Day. And before we get into this week's labs coverage, we'd like to take a moment to honor those who've served. Campus has been full of energy today. The library is packed for pre-final studying, and Miner basketball kept spirits high with the weekend victory over NMSU. Today's focus, momentum and collisions. Our group explored what really happens when two moving objects meet and where the momentum truly stays consistent when energy doesn't. And to start it off, here's Martin with the official lab introduction.
The study of collisions provides an essential framework for understanding the principles of conservation and classical mechanics. When two or more bodies interact, their motion can be analyzed through two fundamental physical quantities, momentum and kinetic energy. Momentum, defined as a product of an object's mass and velocity, is a vector quantity that is conserved in all isolated systems, regardless of the nature of the collision. In contrast, the conservation of kinetic energy depends on the type of collision, whether it is elastic or inelastic, and thus serves as a means of distinguishing between different collision behaviors. An elastic collision is characterized by the conservation of both momentum and kinetic energy, with no lasting deformation of energy lost to heat or sound. Conversely, an inelastic collision involves deformation, heat generation, or the objects sticking together, resulting in a loss of mechanical energy even though the total momentum remains conserved. Understanding the distinctions between these collision types allows for a deeper exploration of how mechanical energy transforms within physical systems. In this experiment, two cards of varying masses are used to simulate both elastic and inelastic collisions on a nearly frictionless track. By measuring the velocities of the cards before and after the impact, the total system momentum and kinetic energy are determined by four distinct cases. 1. Elastic collision with equal masses. 2. Elastic collision with unequal masses. 3. Inelastic collisions with equal masses. And 4. Inelastic collisions with unequal masses. The percent difference between pre- and post-condition momentum and kinetic energy is then calculated to evaluate the extent of conservation in each scenario. This investigation aims to verify the conservation of momentum in all collisions and to examine how kinetic energy varies depending on the nature of the interaction. Furthermore, by analyzing discrepancies between theoretical and experimental results, this experiment provides insight into practical sources of errors such as friction, imperfect alignment, and non-ideal elasticity, emphasizing the connection between theoretical conservation laws and real-world physical behavior.
With the core concepts in mind, it was time to move from theory to practice to recreate both elastic and inelastic collisions. We gathered a few simple tools, each one chosen to measure motion and momentum precisely. Here's Oscar with the materials overview.
Welcome back. Materials used for this lab included 2 Pascal wireless smart cards, a dynamic track, metal weights, magnets, a weight scale, and a Pascal interface with Capson software. The Pascal smart cards were the primary objects for collision, equipped with built-in sensors to record motion data. The dynamic track provided a smooth, level surface to reduce friction and allowed the cards to move freely. The metal weights were added to the cards to vary their mass during collisions, and magnets were used to create elastic collisions by preventing direct contact between the cards. A weight scale was used to measure the precise mass of each card, and a Pascal interface connected to the Capson software collected, displayed, and analyzed the motion data.
Once our setup was ready and calibrated, it was time to put motion into motion. The team positioned both carts on the track, synchronizing their sensors before beginning our first trials. For this experiment, I worked alongside Martin and Chris to align the carts, ensuring the magnets were orientated correctly for both types of collision. Martin took charge of releasing the carts, while I managed the weights and assisted with setup adjustments. Aranza operated capstone with Oscar, monitoring the velocity and momentum graphs in real time. Chris handled the data analysis throughout the process. We began by running elastic collisions, first with equal mass carts, then by changing one to create a mass difference. Next, we repeated the sequence for inelastic collisions, where the carts would stick together upon impact. Most of our technical difficulties came from Capstone itself. Some carts were uncharged, and the interface occasionally lost connection mid-recording. It took several resets and pairings before we could capture clean data, but once everything synced, our collisions ran smoothly. With all 4 collisions recorded, we finally had the data to visualize the heart of this experiment: momentum and kinetic energy before and after impact. Starting with the elastic collision with the same mass, our graph showed nearly perfect symmetry. Both carts exchanged momentum equally, confirming conservation. Next came the elastic collision with different masses, where one cart gained speed while the other slowed, but the total momentum before and after stayed balanced. Then we moved to inelastic collisions with the same mass. Both carts merged right after impact, combining into a single motion. Momentum remained consistent, though the kinetic energy dropped sharply. Finally, in the inelastic different mass case, the data revealed the greatest loss of kinetic energy while still maintaining overall momentum. Each of these results reinforce the key lesson: momentum is conserved no matter the collision type, but kinetic energy only stays consistent in elastic impacts. Once the trends were clear, Chris stepped in to calculate the numerical comparisons, breaking down how close our experimental totals came to theoretical predictions.
In this lab, we recorded the elastic momentum and kinetic energy and inelastic momentum and kinetic energy. We saw that for elastic and the same weight, we had 0.09 momentum, and for the red, the same, negative 0.08 momentum. 0.02 kinetic energy, 0.01 kinetic energy. And then we measured the after for elastic, which we found negative 0.05 for blue, 0.08 for red, and 0.01 for blue and 0.01 for red. And for inelastic, for momentum, we found negative 0.14 for blue and 0.14 for red. And after, they both were 0. For kinetic energy, we found 0.04 for blue and 0.03 for red, and around 0 for both blue and red after, totaling around for elastic 0.01 momentum and 0.03 kinetic energy. For before and after of 0.03 and 0.02. For inelastic, we found around 0 for all of the momentum and kinetic energies. And then we did this experiment again with different weights. So we found that our elastic and the blue with a different weight for momentum was 0.10, and for the red was negative 0.29. For kinetic energy for the blue it was 0.02, and kinetic energy for the red was 0.06. And then after, it was negative 0.16 for the blue, 0.02 for the red, 0.04 for the blue, and around 0 for red. And for inelastic collisions, for the blue cart it was negative 0.14 and our red of 0.29, and our blue of 0.04 and red of 0.06 for kinetic energy. For after momentum, it was around 0, and even for after inelastic, it was around 0. So totaling for elastic momentum was 0.19, and for kinetic energy was 0.08. And after, for momentum was 0.14, and after for kinetic was around 0. Before and inelastic for the total was 0.15, and kinetic energy was 0.1, and after was around 0 for both. Then We calculate our percentage difference by using the percentage difference formula between our elastic and inelastic. And we found that our elastic gave 6.67% for momentum and 3.8 for different weight. And for the same for kinetic energy, we found a 4% difference. And for different weight and elastic, we found a 6.5. For inelastic momentum, the same weight was 40.2. Inelastic different weight was 3.3. For kinetic energy, inelastic same weight was 20.6%, and inelastic different weight was 10.2%.
With the math being finalized and our results confirmed, what did we learn from this experiment? Here's Aranza with the conclusion.
Thank you, Caesar. For this lab, we used a track and 2 cars to see friction. We saw what happened if the cars bounced off of each other. Then, we saw another example where the cars hit each other and got stuck with Velcro. From this, we gathered our data, which was velocity and acceleration, to see our data analysis. We did our best to get the smoothest graphs and finished our lab. Thank you for watching today's episode of UTEP Midday News.
And that wraps up this week's Momentum and Collisions Lab. From perfectly elastic rebounds to the stickiest inelastic impacts, our team saw firsthand how momentum never truly disappears. It just finds a new direction. Even with the occasional uncharged cart or lost connection, the data spoke loud and clear. On behalf of Martin, Oscar, Aranza, Chris, and myself, Cesar Mero, thank you for tuning into UTEP Midday News. Stay curious, keep experimenting, and as always, go Miners.